Over the past few sessions we've been looking at the unit circle and some of the basic concepts. So just to remind you, the unit circle is a circle which has a radius of 1. Suppose we have an angle here theta, then we looked at how we could see that the x-coordinate would be the same as cos theta and the y-coordinate would be the same as sine theta. Using Pythagoras, we could substitute these in and show that sine squared theta, i.e. y squared, plus cos squared theta, i.e. x squared, equals 1. And we also looked at how tan x or tan theta equals sine x over cos x or sine theta over cos x. So we should be familiar with these. What we're going to have a look at today is something called the double angle identities for cosine. So here we've got, again, the unit circle with what you can see are two triangles, ABD and ACD. Now, if we have a look at the two triangles, if we have an angle here which is the same in both instances, so this angle is theta and this angle here is also theta, BD here would be sine theta. We looked at earlier how the y-coordinate is sine theta. We can see that here DC would be sine negative theta. It would be the same size but different magnitude. If we're looking at length purely, then these two would have the same length. So we can say that BD would be the same length as CD, which would be sine theta. We can also see that BC here is the same as BD plus CD. So we can say, therefore, that BC is going to equal 2 sine theta. So we know that BC equals BD plus CD, and we've said that BD is sine theta and CD is sine theta, so sine theta plus sine theta is going to give us 2 sine theta. So we've got one equation here for BC which gives us 2 sine theta. We're now going to have a look at another equation for BC. So if we have a look at angle BAC, so now we're going to be looking at this whole large triangle here. So again, if this is theta and this is theta, the whole angle is 2 theta, which is what we're saying here. Using the cosine rule in triangle ABC, we can say that AB squared plus AC squared minus 2AB times AC cos 2 theta is going to equal BC squared. If we substitute in then, knowing that this is a unit circle, so the hypotenuse here is going to be 1. If we were looking at the right angle triangle, we know that's going to be 1. So substituting in and then simplifying, we end up with 2 minus 2 cos 2 theta. And we can then take the square root of that, so we end up with BC equals root 2 minus 2 cos 2 theta. And this is going to be our second equation. So we've got BC up here is 2 sine theta, and BC here is root 2 minus 2 cos 2 theta. Now that we've got two expressions for BC, we are going to equate them. So we've now got this formula here, 2 sine theta equals root 2 minus 2 cos 2 theta. If we square both sides, we get 4 sine squared theta equals 2 minus 2 cos 2 theta. And we can rearrange that to give us 2 cos 2 theta equals 2 minus 4 sine squared theta by rearranging. And to divide through by 2, we are left with 1 minus 2 sine squared theta. If you are not able to follow that through, have another look, but you're not going to be asked to prove that. What you're going to be asked to be able to do is apply this formula here, or another that we're looking at in a moment. But the takeaway is being able to apply this. So we'll have a look at some examples of how you can do that. Hopefully you can follow that through, but you won't be expected to prove that. So this relationship here, cos 2 theta equals 1 minus 2 sine squared theta, is what we call an identity, as it is true for all of the values of theta. So we're going to have a look now at some different identities for cosine. These are double angle identities for cosine. So this is the the identity that we have just defined. However, we know from previous sessions that sine squared theta plus cos squared theta equals 1. So if we take sine squared theta, we rearrange this for sine squared theta, and then we substitute it into here, we can see that cos t theta equals 1 minus 2 times 1 minus cos squared theta, and we can then expand and simplify that to give us cos t theta equals 2 cos squared theta minus 1. So that is a second form of the double angle identity for cosine. And what we're going to have a look now is at a third version. So if we take this second version here, cos 2 theta equals 2 cos squared theta minus 1. And now if we substitute again, instead of 1 here, we substitute in sine squared theta plus cos squared theta, we end up with this equation here. We can then expand and simplify that to yield a third double angle identity for cosine, which is going to be cos squared theta minus sine squared theta. So the three double angle identities that you need to be able to use and apply are cos 2 theta equals 1 minus 2 sine squared theta, 2 cos squared theta minus 1, and cos squared theta minus sine squared theta. So these are all the same, they will all have the same answer, they are all the same as cos 2 theta. Which one you decide to use, however, will be contingent on the information that you are provided with. So what I suggest we do now is we have a look at practicing an example with these. So at the top you can see that you've got all three identities. Cos 2 theta equals this, or this, or this, depending on the information that you have got available. So given that sine x equals 3/4 and our angle x is an acute angle, find the exact values of cos x and cos 2x. So this question is going to draw on what we've just looked at, but some of your existing understanding of the unit circle as well. And in fact, in a later session, we'll see how it's extended into looking at the double angle identity for sine as well. But for the moment, I suggest you pause and have a look at this question yourself. So to find cos x, we've been provided sine x and told it's an acute angle. So how on earth can we find out what cos x is as an exact value without using our calculator? Well, for this, we need to remember this relationship. Sine squared x plus cos squared x equals 1. If we can remember that relationship, then all we're going to do is substitute in for sine x and square it and rearrange and solve for cos squared x. So cos squared x is going to equal 7 over 16. So therefore cos x as an exact value is root 7 over 4. For cos 2x then, we are going to hopefully recognise that we need to use one of these double angle identities for cosine. The question is which one? Now, if we have a look, we can see that the first one is the only one that relies purely on a value for sine. So in this instance, it makes sense that we substitute in here our value of sine, which is 3/4, into sine x here. So that's going to be 1 minus 2 times sine x squared, which is going to give us 1 minus 9 over 8. And we can therefore see that cos 2x is going to equal negative 1 over 8.